This meeting is being recorded.
All right, so what would y'all like to talk about?
You know, like the E equations, like, one second.
Okay.
Let me see. I think it's like with the exponent ones, it's like E and then it will be like the exponent to like a square root. You know what I'm talking about?
Sure.
Yeah, but like finding the derivative of that.
Something like that.
Yeah, something like that.
Okay. All right, so I want to find the derivative of this thing. Okay. We may have done this exact one in class, but that's okay. So how do we deal with this? So we know that in general, like if this is just e to the x, this derivative is e to the x, right?
Yeah.
Okay. This one's a little different because our exponent is not just x. So I think the way we did this in class was, I'll do it a couple different ways. You know, the first thing that happens to x is that it gets square root taken of it. And then from there, it's going to become the exponent on e. So basically, these are my two steps here. So from there, I can say that e to the square root of x is equal to a composed function, f of g of x, where the outer function, or the function that happens last, is e to the x. I mean, because this little block right here basically just takes whatever comes into it and raises that to the power, raises e to that power. Then the inside function is going to be square root of x. Right. We okay with that so far?
Yeah.
Okay. So from there, I can take derivatives of both of these things. So the derivative of f is e to the x. I'm going to rewrite this as x to the power of a half. And then from there, I can do this. G prime of x equals 1/2 times x to the negative 1/2. So from there, I can start setting up the chain rule. So it's going to take the derivative of the outside function, f, with the inside function left intact, multiplied by the derivative of the inside function. So in this case, that's going to be e to the radical x. Remember, when you're taking the derivative of an exponential function, whatever you started with is going to remain. But in this case, we're going to multiply this by 1/2 x to the negative 1/2.
Okay.
I just got an email that someone else is trying to get in, so let me stop sharing and go help them for a second. Okay. Oh, Adrian's here. All right. So Savannah, you have any questions?
Mine was kind of just the same as like the E things that, but it's the like E plus 3 or the ones that are 3E and it's 3X, which is like more attached to them kind of.
Okay. So with a base different from E, or like do you have a specific one you want to look at?
I can't like view it right now, but it was like the 5th one on the homework, or like 5th or 6th, because it was like E plus, I'm pretty sure it's just X plus 3, but, or E to the square root of X plus 3, but
Oh, okay. So like that?
yeah.
Okay, cool. All right. So looks pretty similar to the one we just did. So how would we handle this one differently? So I still think I have the, the outermost function if I wanted to kind of recreate that or borrow that block diagram again. I believe my outer function is still e to the x. But in this case, my inner function is going to be a little different. It's not going to be square root of x. It's going to be square root of x plus 3. So we know the derivative of f of e to the x is e to the x. Now, the change here is, how do I deal with this square root of x plus 3? So this derivative is going to be, I mean, if you want to think about it, you can think of, well, the outer function here is the square root. Inner function is x plus 3, but I'm going to try to shortcut that a little bit. So basically, I just saw that the derivative of a square root looks like this. So, I mean, we had square root of x before. Now we have square root of this quantity x plus 3. But I still can kind of use that same structure. I'm going to say the derivative of this thing is 1/2 times what's in the underneath the radical to the negative 1/2 power. And the reason I'm saying that is because, we just did this. The derivative of x to the 1/2 is equal to 1/2 x to the negative 1/2. So basically, I'm kind of shortening chain rule here. I don't really have square root of x anymore. I have square root of x plus 3. But basically, the first part of the chain rule is to take the derivative of that outside function, which is kind of what this is. 1/2 times the inside function, which is x plus 3, raised to the negative 1/2. But since I'm doing chain rule, the last thing I'll have to do is multiply this by the derivative of x plus 3, which in this case will just be 1. So I have my derivative of my outer function, my derivative of my inner function, which means I can now take the full derivative. So f prime of g of x times g prime of x is equal to e to the radical x plus 3, because the exponential function will always be included, multiplied by 1/2 times x plus 3 to the negative 1/2. Does that make sense, Savannah?
Yeah. So then if you're given the, like from that step, if you're given the value of x, then do you solve like how like the written problem
Okay.
was with E, and then it had the 2 or 20,000 in front of it. So you'd still find that same one, and then that would be your rate of change, but then you would still plug in, I forget, it was like 3 or 3 point something, 0.3
Yeah,
something
sure.
for X, but so would the derivative A, or would it be the amount that it's increasing? Like, would you write out the equation for A, or would you write out the answer that like would take to plug in? I think it was 4.3, but
What is the exact question that the written homework has on it? I mean, really, the real question is whether, you know, are you being asked for like a value? Like, are you being asked for a rate of change? Like how fast something is happening, at what rate something is happening, or is the thing you're being asked about not a rate at all?
so it asks the balance of the account after the 3 years is like increasing. So,
Okay.
but would that be like how much it increased within that year? Or would that be the derivative function? Because that's essentially how much it's increasing, right?
Yeah, I mean,
Does that
so
make
there's
sense?
there's a couple different things in there. It's kind of subtle. If you're asking about how much it's increased, just by how much it's increased, that does not involve the derivative. If you're asking how fast it's increasing, or something to that effect, that's a question the derivative can answer.
Oh,
So like, I mean, let's give e to the x plus 3 a name. We'll call this h of x equals e to the radical x plus 3. If I want to know what the value of this function is at when x equals 0, then I could just plug in 0 for that. That's basically, that's a point on this curve. That is when x is equal to 0, y is equal to e to the radical 3. But if I want to know a little more information about what's going on at that point, it's like, maybe I don't want to just know where this point is. I want to know like what the slope of the tangent line is, or how fast the function is increasing or decreasing at that point. Then that's where I have to use the derivative. So in this case, it would be e to the square root of 3 times 1/2 times 1 over the square root of 3. So this nasty number we just wrote down, that right there would be the slope of the tangent line. So if I can roughly give a picture of what this looks like, e to the x plus 3 is going to kind of look like, oh, something like this. So that curve that I just drew is, you know, doesn't have a slope, doesn't have the same slope everywhere. It is constantly varying, but what the derivative allows me to do is to find that slope of that tangent line, which is going to be some small but positive number. So, I mean, bottom line, like, I know this is a little hard one to talk about because this, you know, this is just a function without like a real context behind it. But bottom line is focus on, you know, what is the function telling you? And what is the derivative of that function telling you? And it does not matter what the context is, like if it's, you know, you hiring more factory workers, or the total cost of producing a bunch of things, or, you know, all the different situations that we've kind of used as examples. That doesn't really matter. What the derivative really tells you is it's something involving a rate of change. So a function by definition tells you kind of how, as one thing changes, another thing changes with it. The derivative will tell you the rate that joins those two things.
Got it. That makes a lot more sense.
All right, excellent. All right, Adrian, any questions?
No, I just had similar issues with similar problems. I just
Okay.
wanted a little bit more practice with those.
Yeah, no worries. Is there a specific one you want to look at?
Anyone from the online homework, from the logarithmic ones?
Okay. I can't really minimize and go look at it right now, but yeah, if you want to throw
Yeah,
me
I
one,
could
we can do it.
pull one up.
Is anyone with E gonna be knowing that we're using either log or like the chain rule thing? Like there's no other way to solve the E ones, right?
I mean, so so if you ever have something that looks like e to the, or e to the, I'll just put a box here. E to some function, some variable thing, then yeah, you're using those exponential function rules. And by the way, we've talked like specifically like exclusively about E, but that's also true if it's like, 3 to the x, or in all these cases here. So in all these 4 cases, I have some constant number E or 3 raised to something that is variable. So in those cases, you're using, basically this rule. The derivative of a to the x is equal to a to the x times the natural log of a. Or the special case of that where derivative e to the x is e to the x. So yes, whenever you see an exponential function, you're going to use a version of one of those. And in the case where the exponent is something a little more, a little more complicated than just x, then yeah, chain rule is something you have to do. So let's just do an example here. And I'm going to do this one a little faster because it doesn't really work any differently than the 2 we just did. But so this derivative here, so we know that the derivative of an exponential function always contains the original function. So we're going to focus on this top rule here. I know the derivative of a to the x is equal to a to the x times the natural log of a. So the derivative of this is going to be 3 to the 2x squared plus 7 times the natural log of 3. We're not done, but I know my derivative contains that because that's what this rule says. The next part that we have to kind of concern ourselves with is the fact that, well, the derivative of the outside function is this thing. So outer function. I also have to multiply this by the derivative of the inner function, which is 2x squared plus 7. So that is going to be 4x. So even though I didn't like set it up as completely as I did in the last 2 examples, yeah, I still did use the chain rule. I took the derivative of the outside function, which is, basically I got that straight from a to the x times natural log of a. My a is 3. My x in this case is really a more complex function in terms of x times natural log of 3. So there's my outer function. I have to multiply it by the derivative of the inside. So And the question you asked was, do I always need the exponential rules and the chain rule? I don't think there's any way around using these exponential function rules. The chain rule is one of those things that, you know, when you first learn it, it's probably a good idea to really write down what all the different functions are and all the different derivatives and figure out how they all go together. I kind of shortcutted the process because, I mean, I have a lot more experience with it, but also we just did a couple of these that kind of worked the same way. But just to kind of rebuild this, I could very easily have called the outside function 3 to the x and the inside function 2x squared plus 7. Done both derivatives and, you know, set up the chain rule that we kind of done the way we kind of done in class more slowly, and you're still going to wind up in the same place. So basically set this up using as many steps or as few steps as you want, just whatever you're comfortable with, really. Make sense?
Yeah, that's a lot better. Is there any other like cheat sheet rule of like which, I mean, when to use quotient, when to use, I mean, I know when to use quotient, but like the product rule and all the, since like the test is going to be all of them,
Yeah.
is there a distinct differentiation one?
I can give you a quick example here. So let's do this. I'm going to write down two functions. So in this bottom one, e to the x squared, let's follow x and see what happens. What's the first thing that happens to x in e to the x squared? So that first thing is going to be a squaring. And then after that, I take that x squared and I use it as the power to e. So that gives me e to the x squared, which is equal to, now let's call these different things. I'll call this f. I'll call this g. Let's follow the other one. So for f, what's the first thing that happens to x in function f? Well, I mean, there's not really a first thing because, you know, x shows up a couple different ways here. So I'm squaring it, but also like so in this first one, I was squaring x and then using that as the power to e. In this other one, I'm squaring x. I'm also raising e to the power of x. Those two things don't happen one after the other. They happen at the same time. And then what happens to the x squared and the ex? They get multiplied together, and that what comes out is x squared e to the x, which is equal to f. So, I mean, think about the rules we've talked about. We've talked about the exponential rules, exponential function rules. And if you can identify an exponential function, then you know you need to use that. Quotient rule, I mean, if you have a fraction, if you have something divided by something else, and if you can identify that, that tells you you're going to use quotient rule. In my experience, and I'm guessing is the same with all 12 of you in our class, is knowing when the product rule is the thing to use and knowing when the chain rule is the thing to use. So in this top case here, and the thing that I'll ask us to focus on is this. The product rule is about function composition. So, or sorry, the chain rule is about function composition. So if I am using one function as the input to another function, that is the sort of thing the chain rule was invented for. Product rule is if I have two functions multiplied together. So hopefully me doing like these diagrams makes it a little more clear that in this one down here, I have a product because I have this squaring function and this exponential function. I'm finding the product of those two functions. And here in this top diagram here, I really only have one path. So basically I am doing one step squaring and the other step exponential function, one right after the other. This one right here tells me that I am doing a chain rule situation. So, was that the question you were asking?
Yeah, that makes it a little bit better.
All right, cool. Adrian, you were going to look for something from the online homework. Were you able to find anything?
Yeah. I have a problem if you're ready.
Yeah, go for it.
ln and then bracket in parentheses negative 2x plus 5 in parentheses x plus 5.
Okay. Close bracket.
Yeah, close bracket.
Okay. All right. So now we see a natural log, so we know we're going to have to make use of those rules. So the derivative of natural log of x is equal to 1 over x. And more generally, the derivative of any log with any base is equal to 1 over x natural log of a. All right. So I know I need to use those somehow. What can we do here? So we did one kind of like this in class, where the way we handled it is so one thing we know about logs is the natural log of AB is equal to the natural log of A plus the natural log of B. So one thing I could do is this, the natural log of negative 2x plus 5 plus the natural log of x plus 5. If I want, I can rewrite the function I'm given like this and take the derivative that way. So let's actually do that, and then we'll do it a different way to show that as long as everything you do is okay, it does not really matter what order you go in. But now I can start using these rules. In fact, kind of like the ones we did with most of the chain rule, most of the exponential examples, we're going to have to get chain rule involved. So much like those, I believe my outer function is going to be the natural log of x. But what's the thing I'm taking the natural log of? That's going to make up my inner function, which is going to be negative 2x plus 5. Maybe I'll call this f1, g1. So I can call these f2 and g2. f2 of x will be, again, natural log of x. g2 of x will be x plus 5. So is that set up okay? So far, okay with everyone?
Yeah.
Yeah, got it.
All right, cool. Then from there, I need derivatives of all this stuff. So I'll just call it f prime of x, same function, same derivative. We already wrote that down. That derivative is 1 over x. G1 prime is going to be -2. And G2 prime is going to be 1. So from there, can I write down the derivative of, let's call this whole thing h. Can I write down the derivative of h of x?
I am a little confused. How did you get like 4 different points?
Basically, I did this. So first of all, let me ask, I guess I should ask this. Are you okay with how I got from this top step to the next one down?
Kind of. Did you
Okay.
just like separate it by the?
So I separate it using this idea here. And that's something that is true of all logarithms. Basically it's the product rule of logarithms. If I'm taking the log of something that's really 2 things multiplied by each other, then I can take those things individually, those logs individually, and add them together.
Okay.
So that this first step here, right, doesn't involve any calculus. I'm not doing any derivatives yet. I am rewriting the function I was given, hoping that it gives me a derivative that's easier to think about.
Yeah. Okay.
So from there, all right. So from there, can I write down, or can I start writing down what this overall derivative is?
Yeah.
Okay. So I know the derivative of the outside function is 1 over x, but my inner function is not as simple as x. It is -2x plus 5. And then I want to multiply that by the derivative of the inside function, which is -2. So I think that first one is done. Then the next one is, it's going to kind of look the same way. Derivative of the outside function is 1 over x, but with x plus 5 tucked into it. And I'm going to multiply that by the derivative of the inside function, which is 1. So if I want to simplify this, I get -2 over -2x plus 5 plus 1 over x plus 5. So that is one way to do this. I'm not going to go all the way through the other ways you might do this, but you also could do this multiplication. So you get natural log of -2x squared plus 5x minus 10x, so minus 5x plus 25. You could take the derivative of that thing without having to think of it as 4 separate functions. That would also work. Those are probably the 2 most direct ways to get there. Does that make sense, Adrian?
Yeah, thank you.
Yeah, of course. All right, what else?
Could we just do like 1 or 2 more equations using the log? Because I don't know. I'm kind of struggling like deciding what like rule you're supposed to use for what equation.
Yeah,
That
sure.
makes-
So let me ask you this then. What like in this one we just did here, like what decisions are you talking about that would have been tricky for you to make?
Like I don't know. I just
Okay.
like don't get it.
Okay. Do you have a specific example you wanted to talk about for like a log one?
Let me look.
For the last problem, I think when I was clicking on like through the help part of the homework, I
Mhm.
think it had me work it as the ln close bracket negative 2x, where you like multiplied them together and then you got the derivative.
So you had to do this.
Yeah.
Okay.
But I got a different answer. It was I got 4x plus 5 over 2x minus 5 multiplied by x plus 5.
Over 2x minus 5 times x plus 5.
Yeah.
How'd you get this right here?
That's out because that's what I was kind of wondering, because I was like kind of clicking through, like I was clicking through like to help me through the steps.
Okay.
And then that's what it said it was right. So I don't
Okay.
know.
So basically, I'll show you where this answer comes from so it's not mysterious.
Okay.
But I'll kind of shortcut it a little bit because we've already, so the way we did this here, we know that the natural log of the derivative of natural log is 1 over, the derivative of natural log of x is 1 over x, right?
Yeah.
But more generally, we know this, the derivative of the natural log of something is going to contain 1 over that something, right?
Mm.
So I know this derivative right here is going to contain 1 over this. Does that make sense so far?
Yeah.
So basically that thing I just wrote down right there is the outer, like kind of the first step of the chain rule. I took the
Okay.
derivative of natural log of my inner function with the inner function left alone. So then the second part of the chain rule is to multiply by the derivative of this inside function. So that is going to be negative 4x minus 5, right?
Yeah.
Okay. So here's how they got from where we are now to where they ended up. Basically what they did is, so you have negative 4x minus 5, right?
Yeah.
What they did is they factored out a negative 1 and then changed both of these to positives.
Okay.
And then they basically did the same thing in the denominator by factoring a negative 1 out of negative 2x plus 5. All these signs get flipped too, so that becomes positive 2x minus 5.
All right.
And then negative 1 in the numerator cancels negative 1 in the denominator. So I do that to show you where this thing came from.
Mm-hmm.
But basically everything I did after I wrote down like the derivative of the inside function is kind of, if I'm asking for the derivative, we were done a long time ago.
Yeah.
The rest of that was just them just kind of trying to simplify and make things positive and things that if you want to do, go for it. But if I don't tell you to simplify a derivative, if I just want you to find it, then that's kind of what I'm after.
Yeah. The way we did it together just before this was way easier than.
Yeah. So the way we did it
Yeah.
together, I mean, we did it totally differently than the way they did it.
Yeah.
But like, you know, ignoring all the stuff I've crossed out and stuff, this derivative right here is fine. Yeah, it doesn't look that great, but I mean, I at this stage, I am mostly concerned with with you all being able to find derivatives and then use them for, whatever they say. The simplifying thing, it's valuable to do, and it makes your work kind of easier to see at the end. But yeah, right now I'm focused on this new thing, which is this act of taking derivatives and interpreting them.
Okay.
Abby, were you able to find something?
Yeah, I don't remember if this was from like the notes or the homework, but I'm sure we've done it at some point. But
Okay.
it was just like d over d of x and then the natural log ln. And then it was like 3 in the square root of x plus 5, if that makes sense. So it was like the little 3. I don't know what that's called. You know what I'm
Oh,
talking-
log base 3. So does it look like this?
No, it's like here, wait, I'll try to like show on the camera.
Okay.
I don't know if it's gonna, oh man.
Camera's off. That's good. Try to describe it again. I'll get it.
So it's like oh man, can you see that? The 3. Oh, it's kind of blurry. Oh
The
man,
natural log of the square root of x plus 3.
I don't know. Oh yeah, but then x plus 5. So it'll be x plus 5, and then the little 3 goes like right outside of the square root, if that makes sense.
Oh yeah, that's a cube root. Okay, yeah,
Okay.
like that.
Yeah.
Okay. All right, so let's handle this a couple different ways, because one is, I mean, they're both fine, but if one makes more sense to y'all than the other, awesome. So let's start by doing this. What is happening to x? What happens to x first?
It gets added to 5.
Yeah, so first we increase by 5. After we add 5 to it, what happens to it from there?
It gets in a square root, or
Yeah, so cube root. But yeah, so that happens next. The cube root. So what comes out of there is the cube root of x plus 5. And finally, I get the natural log of that. So I get the natural log of the cube root of x plus 5. And that is equal to, we'll call this f. Okay. So I think we did this one in class, but it's worth kind of revisiting. That cube root. So by the way, like just to kind of give you a more basic reminder here, when we do things like the derivative of the square root of x, I mean, unless you have it memorized by now, which is not necessary, I mean, kind of the first way we handle that is to write this out as x to the 1/2. Because that lets us use the power rule, which is something that in derivative square root of x is not like, we don't have a rule for that. I mean, we kind of use the power rule to handle roots. So what I recommend doing with square root, cube root, any root is to rewrite them so that I can think about this as the natural log of x to the 5th to the 1/3 power. So that is that's a key thing that I would focus on, is that, I may have even written this on the board the other day, but that if you have a root of x, like the 8th root,
it's just 1 over that.
yeah, x to the 1/a power.
Oh, that's like really easy. Okay.
Yeah, so Yeah, I mean, if that's again, I know this is something you've all seen. It may not mean it's one of those things that's kind of remains mysterious, especially if you haven't seen it in a while, but I know you've all seen it. But this idea here is really powerful for, making the chain rule accessible to you. So now we have the natural log of x plus 5 to the 1/3 power. So we have a couple different options. I'll do what I think is the longer option first. If we take the derivative of this, let's see, what's my outermost function? My outermost function is natural log of x. I know the derivative of natural log is 1 over whatever came into it. So in this case, it's going to be 1 over x plus 5 to the 1/3 power. Then I have to multiply by the derivative of the function that led into it. Sorry, or yeah, basically I have to keep following the chain rule from the end all the way back to the beginning. So derivative of natural log is 1 over x plus x, 1 over whatever the function that led into that is. So now the next thing is I got to take the derivative of the next one. So that's going to be 1/3 times something to the negative 2/3 power. Are we okay with where that came from?
Yes.
So this right here, basically, I'm going to make these dots even bigger so I can really keep all these things separated from each other. The derivative of the outermost function times the derivative. So sorry, I'll start over. The derivative of the outermost function with the actual input to that function left intact times the derivative of the middle function with the inside function or the output of the inside function left intact, multiplied by the derivative of the innermost function, which is 1.
So you basically just take the derivative of each part and multiply it together.
That is what the chain rule is.
That's okay.
The big thing to pay attention to is, I mean, yes and no. I mean, your question was, it's just the derivative of each part multiplied by each other. It is that, but maybe the most difficult thing to keep track of is what the inputs to all those functions are. For example, it might be tempting to say, all right, the derivative of natural log is 1 over x, so 1 over x. The derivative of the cube root is 1/3 times x to the negative 2/3. So this is a problem because you're trying to do too many steps at once. When you do the chain rule, you need to be careful about what the inputs to your functions are. Derivative of natural log of x is 1 over x. But in this case, my input to this part of this function is not as simple as just x. There's more to it than that. In this case, it's the cube root of x plus 5.
Okay.
So this right here, and I'll do this just to kind of illustrate something else. I have 1 over x plus 5 to the 1/3 times 1/3 times x plus 5 to the negative 2/3. This is all right here going to work out to be 1 over 3 x plus 5 times x plus 5. Because if I were to take this negative exponent, I'll kind of break this off to the side here. 1/3 times x plus 5 to the negative 2/3 is equal to 1/3 times 1 over x plus 5 to the positive 2/3. And then when I multiply that, so x plus 5 to the 1/3 times x plus 5 to the 2/3 becomes x plus 5 to the 3/3. So it's power of 1. The other way to do this derivative is like this. We already showed the natural log of the cube root of x plus 5 can be rewritten as natural log of x plus 5 to the 1/3. It can also be rewritten like this: the derivative of 1/3 times the natural log of x plus 5. Because one of those log properties we have is this: the natural log of, I'll say this more generally, log base a, does not matter what the base is, of x to the power of y is equal to y times log base a of x. So basically, if I have an exponent in the thing I'm taking the logarithm of, then I can bring that exponent down and just multiply it by the log of, whatever the original base is. So if I take this derivative like that, then I get, and it's going to be 1/3. That's a constant multiple, so I can just kind of carry the 1/3 with me, times the derivative of natural log of x plus 5, which is going to be 1 over x plus 5, times the derivative of x plus 5, which is just 1. So that's still going to come out to be 1 over 3 times x plus 5. So one thing to kind of look out for is this idea that, just because you can take a derivative, maybe there might be something you can do that'll make it simpler. So in this case, bringing down that 1/3 as a multiplied constant instead of a power made things, a lot faster to deal with. And I think when we did this one in class, we did not go through this one a long way. I think we just did I just showed you could bring it down and do that derivative. All right, any questions there?
No, I got it now.
All right, cool. All right. Archie, you have anything?
I was gonna see. Well, we already went over like logarithm functions. I think, right? And
Yeah.
did we go over like all the applications of how to use it, not just the chain rule, or?
I think we've focused on chain rule. We do a product rule one. Now we kind of worked around the product rule one. I will remind you that because of the way logs work, you can sort of avoid things like the product rule. Not avoid, but in this case, we definitely could have done this using the product rule.
Okay.
But that's kind of like just to show that logs kind of have these things baked into them that you can rewrite them in certain ways. So you can, in this case, we kind of got around the product rule. In the one we just did, where is it? Oh, in this one we just did, the first way we did it, we kind of did this complicated chain rule with 3 layers in it. But if with a rewrite, you can avoid, I still kind of use the chain rule, but it was much simpler if we start with that rewrite.
So it's not like avoiding the application. It's more like minimizing the amount of times we have to use it.
Yeah, right. So basically, I did a little bit of algebra before I started the derivative to make the derivative a little simpler to do, or in this case, probably more than a little simpler. It's pretty fast.
Okay. And for the cheat sheet, because I know we're supposed to have for the cheat sheet, it's good to have example problems of how to approach chain rule and the different derivative rules. Do you think it would help to have the different derivatives of the natural log functions, natural log this is 1 over x and stuff like that?
I would definitely have this. Yeah, so I mean, and I think I was gonna rewrite it, I was gonna write them down again, but I think I've written them down before. I would definitely include things like this.
Okay, let me just. Because I wasn't sure like how in depth we're gonna go into that on the midterm.
Oh yeah, I mean, that's all, I mean, anything I've asked you about, anything we've talked about between, day one and last week is fair game, so.
God. Got you. Okay.
So I mean,
so
we
I'm
did, yeah,
guessing-
the log, I mean, pretty much all we've talked about today has been the log and exponential function stuff, because I
That's
suspect
the newest stuff.
that's the newest stuff. But, for example, I would not, if I were y'all, I would not try to remember in the moment what the quotient rule looked like.
Okay.
Because quotient rule is one of those things that, even at my experience level, I'm only like 80%, 80% confident in my memory of it.
Yeah, the only
Um,
reason the only reason I remember the quotient rule, I just remember it's like the product rule, but then it's like x squared at the bottom because it doesn't matter
Yeah.
what we multiply.
Right. But just for me, like, I still kind of have that lingering doubt as to, it's like, is that really the one that goes first? Because with the quotient rule, the order matters. So all that to say that if I'm giving you the opportunity to make a reference sheet, I would include all those things on there.
Got you. Is there anything from like the slides that like in like the modules that you think would help, or
Most of the things that are in the modules are the things we do in class. But I mean, it's worth looking into. One thing I probably should remind you about right now is that all the quizzes you've done, I've posted solutions to the first 6 of them. There's a module called, I think it's called written solutions or something.
oh, I didn't know.
Oh, not
that.
quiz solutions. I've given solutions to the written homeworks.
Oh, okay. Gotcha.
So those are there. Those are probably worth looking at, even if you did well in the written homeworks. Just because maybe I did it differently than you did. But in terms of the things that are in those modules, I really just use the modules in there to collect the things we've done in class and to highlight due dates for the things I'm assigning. So if you go look through those modules, there's probably not a lot new there. The last thing I'll bring up is that, if you haven't already looked at it, I posted a document that has a bunch of
review problems.
review problems from the book, like way more than you should actually be doing. I mean, there's a lot of things from the book that are good warm up. I don't think it's worth your time to do every single one of the things that I identified, but just to kind of give you some practice.
Okay. Yeah, I was about to like go over them today. I wasn't sure like how I was gonna approach that. Like, would it be better to like just try to do as much as I can? Would it better just like try to do a piece from each section?
What I would do is, just start looking at them and if you start a problem and you're like, I know exactly how this works, then just don't do it. Those are, I like put those problems together kind of as a diagnostic for y'all to figure out what you need to work on.
So it's like what's it called? Almost like a placement test to see what our weaknesses are.
Yeah, maybe. I mean, there's probably the questions at the back of those, like kind of like, at the back of those sections are probably more complicated than anything I could ask you on a test because they're just long, but the concepts are all there. The techniques are all there. So if you feel if you feel comfortable with them, then I would feel good about tomorrow.
Gotcha. And it's like the quiz is the whole class, 100 points, and I think like how many, like 25 questions or
I think it's 7 questions.
oh 7? Oh dang.
Yeah.
Oh, I thought it was
Well, like
man.
it's but questions have multiple parts. Partial credit's a thing as long as I know what you were thinking. As long as you're on the right track. There's no multiple choice. I don't like doing that kind of stuff. But yeah, don't get spooked by the fact there are so few questions. That's kind of a common thing especially when you get into calculus and when you get into classes where like you're doing a lot of interpreting. Like if all I was having you do was take derivatives, hopefully it's not like a surprise to say there are going to be derivatives on this test tomorrow. But if
Yeah.
all I was asking you to do was to take derivatives, I could probably ask you 25, give you 25 functions and ask for derivatives. But think about the things I've been emphasizing in class. Like, yes, it's important for you to know how to take a derivative, but it's more important to me that you know what that thing means.
Got you. So
Like,
that's why.
If we have a function that kind of it describes the total cost of producing, some number of items, what's the derivative? Then what is if that's what the function says, then what does the derivative tell you? If I ask you for the derivative at a certain point, what does that derivative tell you about that certain point? So, yeah, we've done lots of examples like that. Pretty much all of the written homeworks have kind of been interpretation heavy.
Right.
So I would go look at those solutions and make sure that your interpretations are good. But when I brought it up a couple weeks ago that people were kind of like, telling me that the derivative tells us something that has nothing to do with the rate of change.
Oh yeah, I remember that.
Yeah. So that I feel like has gotten a lot better. But yeah, in short, know what a derivative tells you.
Okay.
All right. What else?
What if we like kind of quickly went over like the limits on like the graph and like the continuity and stuff like that? Because I don't exactly remember all of that.
Okay. So specifically on a graph.
Yeah, and just like, here, one sec.
All right. So let me ask you a few questions here then. What is f of 3? What is f of 7? What's the limit as x approaches 3 of f of x? What's the limit as x approaches 7 of f of x? Yeah, so can we come up with values for all these things?
Wouldn't f of 3, I'm guessing, would be 5.
F of 3 is equal to 5. Why 5 and not 2?
Because 5 is where the closed circle is, and the closed circle is a defined point, while open circle is an undefined point.
Okay, good. How about f of 7?
Wouldn't
Is
it like,
that- Oh,
oh no, Abby, you got it.
Go, Abby.
is it 2?
It's 2.
Oh, yes.
Okay.
Yeah, I felt that. I was like, is it 2 or is it like undefined? Then I remembered like it doesn't matter that that point's not defined. It's the way it's approaching that matters.
So let's ask this question then. Let's skip the third line for now. What's the limit as x approaches 7 of f of x?
Now that would be 4, right?
That's 4.
Yeah,
And what about the limit as x approaches 3?
that's undefined.
That doesn't exist. Because, and we can get a little more specific with this one, we can talk about the limit as x approaches 3 from the left and the limit as x approaches 3 from the right. So what are these two limits here?
Well, x approaches 3 from the left would be 4, and from the right would be 2. Oh, wait, not 4, it'd be 5, and then from the right would be 2.
Right. So this is why the limit doesn't exist. Does that sound familiar?
Yeah, like
So-
that's one of like the continuity rules.
So continuity relies on a couple things. Really, so let's do this. So I'll say f is continuous at a if the limit as x approaches a of f of x is equal to f of a. So this thing right here, this very like short statement is where continuity comes from. The thing I approach around a point and the value I actually have at that point need to agree. So in that case, is my function continuous at x equals 3?
No.
No. That okay, is it continuous at x equals 7?
Yeah.
Yeah, I gotta vote for yes.
Yeah.
All right, what's the limit as x approaches 7 of the function?
4.
What is f of 7?
2.
2.
So not continuous here, not continuous. And this is kind of tricky things. So the limit exists there, but that's not enough for continuity.
Oh
limit-
yeah, it needs to be an existing, and the limit has to be defined
Right.
there.
Yeah. So basically both these points 3 and 7, I don't have continuity. I think at 3, I mean, it's a little easier to see because the limit just fails to exist.
Yeah, and there's like a visual break in the graph.
Right. That break is not as obvious at 7. But like, so right now, this function I've drawn is continuous everywhere else. So let's look at this point here. Let's say this right here, this point is 6, 3. What's the limit as x approaches 6 from the left? The limit as x approaches 6 from the right? And what is f of 6?
So there'll all be 3.
We okay with that? They're all 3? And just to kind of mimic my, because these left and right limits agree, that means the limit as x approaches 6 of the function is also 3. So I have the limit of the function exists at that point. The function is defined at that point, and those two values are the same. So I have to have continuity there. So not continuous at 7, not continuous at 3, yes, continuous at 6.
Okay. Oh yeah, for like is there any like questions on like on the test that are going to be like graphing questions, or like where we're gonna have to graph the continuity, or we're just gonna have to interpret it?
I would be ready to do both.
Okay.
So like we had a written homework like that, right?
Yeah.
yeah, at least, yeah, make sure that, I mean, that one was kind of tricky because the thing I asked you has, there's lots of solutions to it. And I really can't, I can't show you all of them, obviously. But I do think the way I did it is probably different from the way that any of you all did it. So, I mean, that one might be worth looking at, but one thing I'll focus on is that, so this is a pretty, this little statement here is pretty loaded. So what's typically done is this is broken down into 3 ideas. The limit as x approaches a of f of x exists. F of a exists. And then what's the final idea? If those 2 things exist, what's the last thing I need for continuity? So basically the left-hand side of this equation exists. The right-hand side of this equation exists.
And they have to be equal to each other.
Right, and they agree. And that's exactly why we said continuity did not exist at 3 and 7. So at 3, the top line fails, right?
Right.
For 7, top line is good, middle line is good, bottom line fails. And then x equals 6, top line exists, top line is good, middle line's good, bottom line's good. So all 3 of those conditions are met.
Okay, so limits, continuity, derivative rules, logarithmic rules, and then there was like that special rule that applied for only E, I think.
Only what?
Like only like the variable E, like it had its own set of rules, right?
I mean, just the derivative of an exponential function. Yeah, here you go. I mean, these are, I kind of gave them to you as 2 different rules, but really it's one rule with a special case that is worth talking about. But the derivative of any exponential function is equal to that exponential function times the natural log of the base.
Gotcha.
And for e to the x, that's still the same. It's just that natural log of e is equal to 1.
Oh, okay. Is there anything else that like comes to mind that you don't feel like we touched, like we don't feel like we touched enough on in like the meeting? Because I did turn in like the meeting pretty late.
Yeah, I mean, the only, like, of the differentiation rules that we've gone over, the only one I think we haven't done an example of is quotient rule. I don't think we have time to do one in the last minute here, but I think I suspect the reason that nobody asked about a quotient rule one is because as far as all the situations you might use the derivative rules, quotient rule kind of jumps out at you.
Oh
If you
yeah,
ha-
because it's usually set up like a fraction, right?
If you have division, that's simpler to see. I think I did an example here where like chain and product rules are, they can be confusing as to about when to use which one. So I went over that a little bit. But I think the quotient rule was the only technique we didn't really talk about. We didn't talk about a lot of interpretation stuff. So if that's shaky for you, I would go look at some of our like more recent written homeworks and make sure those kind of things make sense to you. Otherwise, I think we hit a lot of the big picture things.
Oh yeah, there's another thing I wanted to ask, but it's not about like this midterm, it's about like the other midterms or like the preceding midterms that are coming up like later in the semester. Are they going to be focused on like the chunk of things that we've done like leading up to that like not including what we've done leading to the first midterm, or is it like everything leading up to it?
I mean, they're not going to be comprehensive. Like, the next midterm will be about the stuff that happened since this one. But like, you know, taking derivatives using the power rule is never going away. Taking derivatives, like interpreting derivatives, is never going away. So those kind of things are going to hang on. So I mean, in some ways, there's going to be some stuff from the first midterm, but yeah, it'll be more focused on the new kind of things we do.
Okay.
But like
Gotcha.
we covered taking derivatives in this chapter, or in this unit, so we're not done doing this.
Right.
All right, I think that's time. I am going to yeah, I'll post this video online if you showed up late and want to see what you missed. But yeah, otherwise I'll see you all tomorrow morning.
All right. Thanks, Professor.
Yeah,
Thank you.
you.
Of course.